You ever stop to think about how our digital world just works? I mean, you tap a button, a car shows up. You post a photo, and boom, thousands of people see it in an instant. We've gotten so used to this idea that everything is always on, always fast, and always works perfectly. But behind that magic, there's a massive engineering challenge. Today, we're going to pull back that curtain.
You know, this quote from the legendary computer scientist Alan Kay just hits the nail on the head. Our technology feels as natural and ever-present as the ocean. And that's exactly why it's so jarring when things go wrong, when an app freezes, a website crashes, or our data just vanishes. That smooth, calm surface hides some incredible and sometimes chaotic complexity.
So what's really going on under the hood? Well, the game has totally changed. It used to be that the biggest challenge for apps was raw computing power. We called them compute-intensive, but not anymore. Today, nearly every app is data-intensive. The real fight isn't about CPU cycles, it's about handling huge amounts of data, ridiculously complex data, and data that's changing at lightning speed. It's a whole different ballgame.
Which brings us to the big question, right? Why is it that some systems can handle millions of users and never even break a sweat, while others seem to fall apart if you just look at them wrong? What's the secret sauce? Well, I can tell you it's not some magic tool or a secret programming language. It's a philosophy.
It's a philosophy built on three fundamental ideas, these three pillars. First, reliability, which is all about how you survive when things inevitably go wrong, because they will. Second, scalability, which is about how you cope with success and growth. And third, maintainability, which is all about making sure the system can be understood, fixed, and improved for years to come by the actual humans who have to run it. All right, let's dive into that first pillar, reliability. This is all about looking into the future, anticipating that things are going to break, and building a system that can take a punch without going down for the count. So, what do we actually mean by reliability here? It's pretty specific. It means the system keeps doing what it's supposed to do at the level of performance a user expects, even when parts of it in the background are going haywire. Okay, now this next part is super important. We've got to get the lingo right, because there's a huge difference between a fault and a failure. A fault is when one little piece of the system messes up. Let's say a single hard drive dies. A failure is when the entire service goes down for the user. See the difference? You can't prevent all faults. That's impossible. The real goal of a reliable system is to be fault tolerant. You want to stop those little faults from ever causing a big, catastrophic failure.
And believe me, faults come from literally everywhere. Hardware? Oh yeah, it breaks. All the time, especially in big data centers. Software. It's full of sneaky little bugs that can hide for years before some weird event brings them out. And of course, us, humans, we make mistakes. In fact, one study found that simple configuration errors, basically an engineer typing the wrong thing, were the #1 cause of outages for major internet services. So a reliable system has to plan for all three.
So let's say you've built a super reliable system. That's awesome. But what happens when it gets popular? Like really popular? That brings us right to our second pillar, the challenge of scalability.
And if you want to talk about scalability, there is no better case study than Twitter. Their biggest headache wasn't just the sheer number of tweets being sent. No, it was this monster problem they called fan-out. Imagine the celebrity with millions of followers. They post one little tweet, and boom, in an instant the system has to deliver that single tweet to millions of different timelines.
This forced their engineers into a huge architectural choice. They had two main options. Option 1, do all the work at read time. So when you open the Twitter app, the system scrambles to find everyone you follow, grabs all their recent tweets, and mashes it all together for you on the spot. Or option 2, do the work at write time. The second that celebrity hits tweet, the system frantically finds every single follower and pushes that new tweet into their timeline cache, their own personal inbox. So which one would you choose? Well, let's put some numbers to this. On average, Twitter was handling about 4,600 tweets every second. Now, don't get me wrong, that's a ton, but for a modern database system, it's manageable. But here's the kicker. Because they chose that write time strategy, that fan-out effect meant those 4,600 tweets per second exploded into, get this, 345,000 writes to their timeline systems every single second. That massive amplification, that is the scalability nightmare in a nutshell.
Okay, so just handling that fire hose of data is one thing, but how do you even know if you're doing a good job? You have to measure your performance, and this is where a lot of people get tripped up. Just looking at your average response time is incredibly misleading. It can hide some really serious problems. The real story, the important story, is in the outliers.
This is why the pros don't just look at averages, they look at percentiles. The median, or P50, that's your typical user's experience. But what's really interesting is the P95 or the P99. That tells you what the experience is like for the slowest 5% or 1% of your users. That worst-case performance is often called tail latency, and it is absolutely crucial.
And here's why you should care. This quote from Amazon just says it all. Think about it. Who are the people having the slowest experience on your app? A lot of the time, they're your power users, the ones with the most friends, the most posts, the most data. In other words, they are your most valuable customers. So if you ignore that tail latency, you're literally giving your VIPs the worst possible service. Not a good look.
So a system can be reliable, it can be scalable, but we're forgetting a key ingredient: us, people. A complex system isn't something you just build and walk away from. It's more like a garden that has to be tended to, fixed, and improved by humans for years. And that brings us to our third and final pillar, maintainability. Now, maintainability is often the forgotten pillar, but it's where most of the real-world costs of software comes from over its lifetime. It really breaks down into three big ideas. First is operability, making it easy for the operations team to keep things running smoothly. You want a clean dashboard, not a tangled mess of wires. Second, simplicity, fighting back against complexity so that a new engineer can join the team and actually understand how things work. And third, evolvability, making it easy to change things later on because, trust me, requirements always change.
So what's the best tool for all of this, especially for simplicity? It's a concept called abstraction. And all that is a fancy word for hiding complexity behind a simple interface. The pizza example is perfect. When you order a pizza online, you just click Order Now. You don't need to know the IP address of the pizzeria's server, or the optimal baking temperature, or the delivery driver's route. All that crazy detail is hidden. The button is the abstraction. Great systems do the exact same thing for engineers, making their lives possible.
Okay, so let's bring it all home. Reliability, scalability, and maintainability. The key thing to get is that these aren't separate goals you choose from a menu. They're deeply connected. Together, they form the foundation of pretty much every digital service we rely on.
So if you walk away with just one thing today, let it be this. Reliability is about designing for a world where things break. Scalability is about having a plan for your own success so it doesn't become your downfall. And maintainability is about never forgetting that at the end of the day, humans have to build, operate, and fix these systems. And designing for them is just as important as designing for the machine. So next time your favorite app freezes up or a website just won't load, you've got a new framework to think about it. Ask yourself, what just happened here? Was this a reliability problem? Did something break that the system couldn't handle? Was it a scalability problem? Did a sudden surge of users just overwhelm it? Or maybe, just maybe, was it a maintainability problem? A sneaky bug that got in because the system was just too complex to manage? Which pillar do you think just crumbled?